So today we're going to do a little bit of review stuff before we dive into Chapter 7. Mostly because Chapter 7 is like an extension of things that you would have done in your geometry class and some ideas that we used in first semester. So I want to make sure that we can... all that stuff was a long time ago, so I want to take a little bit of time and review kind of the jumping off point and kind of show how Chapter 7 fits into the stuff we've kind of already done, just to make sure that we're all kind of on the same page starting at the same spot. I know that geometry was a long time ago for a lot of us, right? So one of the main ideas that we're going to be talking about in Chapter 7 is this idea of solving a triangle. When we say solving a triangle, what we mean is we want to figure out the lengths for all of the sides and the measures for all of the angles in the triangle. Now, this is a task that we've already done in your geometry course, but we only did it for right triangles in your geometry course. So that's kind of where we're going to start today, is just reviewing how we did this with right triangles in our geometry course and talk about some of the tools that we use to do that and do some examples of doing that. And then we'll start extending this out to how we would do this for any triangle. Okay. So let's think back to our geometry course and think about some of the tools that we had available to us to use with right triangles. What are some things that were true that we could do with right triangles? I know I'm asking a lot because it was a long time ago. But there's still things that we used in first semester here this year. So there's 3 things on this list that I'm looking for. Jay. Okay, so we know that a right triangle has a 90-degree angle, for sure. That wasn't one of the things that I was looking for, but that's absolutely true, and that's an important fact to remember. What else do you know about the angle measures in a triangle? They add up to 180. Now, that's true for any triangle, not just right triangles, but let's write that down, because when we solve triangles, that was certainly something that was useful to us. So the sum of interior angles is 180 degrees. And that's true for any triangle, not just a right triangle. There's 2 other tools that we would have used here that were specific, though, to right triangles. Both of them are things you are very familiar with. And when somebody comes up with the name, you're going to go, oh, yeah, I know what that is. One of them's a theorem with a specific name. Landon? Yeah, the Pythagorean Theorem. Very good. Right, where it was a squared plus b squared is equal to c squared. That's the Pythagorean Theorem, right? We all remember that, I hope. What's the important thing that we have to remember about the a, b, and c in the Pythagorean Theorem? C is the hypotenuse. Excellent, yes. Okay, very good. The other tool that we're thinking of is an acronym. Sohcahtoa is the one that I was thinking of. That was the one that's specific to solving right triangles, although PEMDAS is an acronym that we use in mathematics. And remember Sohcahtoa, what is that really describing to us? Yeah, it's giving us the definitions for sine, cosine, and tangent in terms of ratios of side lengths in a right triangle. So the SOH tells us sine of theta is opposite over hypotenuse. CAH tells us cosine of theta is equal to adjacent over hypotenuse. And TOA tells us tangent of theta is equal to opposite over adjacent. Right? Do you guys remember those? We don't need to write that out again. We're good with just the acronym. Okay. If you change your mind, holler at me. We can certainly do that. But my experience is that that's not something that fades real bad. Okay. So let's do a couple of examples now. We'll do two examples because there's basically two types of problems that we can have, or that you guys would have dealt with here. Name these things. So let's say that we have a right triangle and we're given one other angle measure and one side length. Okay? And what we're asked to do is to figure out the other pieces. So we need to figure out angle B, side BC, and side AB. If we're going to solve that triangle, we need to figure out those three pieces. Everybody happy so far? This look familiar as a thing that you would have done in geometry. Should hopefully ring some bells, although I would not expect you to be able to do it with no example or no refresher. Okay. Now, first things first, it doesn't matter which piece you want to solve for first. You don't have to do this in any specific order. It's going to be fine, any order that you want to do it. It's going to be fine. The algebra, like the work, would be a little bit different depending on what stuff you knew or what you did first, second, and third. But it doesn't matter what you do first, second, or third. You know what I mean? Okay. So let's just go straight down my list here. We'll do angle B, and then we'll do BC, then we'll do AB. Sound okay to you guys? The order doesn't matter. Let's just do it in the order I wrote it down. How do we find angle B? Landon. Good. Yeah. So we're just going to use that third bullet point. So 180 minus 90 minus 43 is going to give us whatever angle B is. Everybody happy there? Cool. Now let's figure out side BC. So the first thing I'm going to do is I'm going to pick one of the two non-right angles to use to find this side BC. Does it matter which angle I pick? No, but the work is different depending on which angle you choose. For the sake of argument, let's choose the 43 degrees. We could certainly have used the 47, but doesn't matter. So relative to that 43-degree angle, BC, the side we're looking for, is that opposite, adjacent, or hypotenuse? That's opposite. And the side that we know, the 10, is that opposite, adjacent, or hypotenuse? Adjacent. Now, any question about how we figured out which one was opposite and which one was adjacent? Okay, very good. So if I have adjacent and I want to find opposite, which trig function do I need to use? Sine, cosine, or tangent? Tangent, right? because tangent is opposite over adjacent. So we would write tan 43 is equal to opposite over adjacent. Feel pretty good? Okay. So to solve for BC, I got to get the BC by itself. So what should I do? So I'm going to solve this equation for BC, right? So, yes, Landon. Very good. Yeah, we'll multiply both sides by 10. That'll get the BC by itself. Everybody happy there? And now it's calculator time. So I'm going to type in 10 times tan 43 into my calculator. What do I need to worry about, though, before I type this into my calculator and press enter? What mode am I in? Very good. Remember last semester we were sometimes in radian mode, sometimes in degree mode. Got to make sure that we're in the correct mode before we type this into our calculator. What mode should my calculator be in for this problem? Degree or radian? Degree. Great. How do you know degrees? Because the problem has degrees in it. Excellent. That's simple, right? Okay. So let's check our mode real quick. I am in degree mode. So just do 10 times tan 43. And that comes out to 933. So far, so good. Okay. How do you want to solve for AB? You could use the Pythagorean Theorem. Great. So how do I write the equation then? Or what equation? How do I write that? Okay. I'm going to write it as AB squared because that was the name we gave it, but sure. Everybody happy there? So to get the AB by itself, what do I need to do? Because right now I have AB squared. Well, I want AB. I have AB squared in my equation. So what do I need to do? Yeah, square root both sides, right? Now, a couple of things to keep in mind. 10 squared plus 9.33 squared is not 19.33 squared. You're violating the order of operations. You can't add before you do the squaring. The second thing is the square root of 10 squared plus 9.33 squared is not just 10 plus 9.33. Square roots do not distribute. So the way I want to type this into my calculator is basically exactly as it looks on my sheet of paper. Oops. And I'm going to use the ANS function to just retrieve that 9 point whatever so I don't have to worry about typing all those decimals. So I get 1367. So far, so good. Now, there's another way you could have done this. The other option that you could have done is you could have done the same thing that we did to find BC. So I could say that here I'm looking for hypotenuse, and I know the adjacent. So I would want to use cosine. right? Is everybody okay with that setup? So to solve this, because the AB is in the denominator of my fraction, the first thing I need to do is get it out of the denominator. So we'd multiply both sides by AB. And then divide both sides by cosine 43. And you'll see that I get the exact same result, right? As long as I used all the decimals from the 9.33 when I did the Pythagorean theorem, I'll get the same result doing it this way. If I had rounded, the numbers will differ a little bit because of the rounding. Is that okay with everybody? Okay. The other way that this problem could be appear is if we just give you two side lengths and no angles. Everybody's okay with that's what we're looking for? Okay. Once again, it doesn't matter the order in which we do these things. So again, the arithmetic will be a little bit different depending on the order that you do things, because what you know or you don't know. But it doesn't, like, you can still do it. You know what I mean? So which one of these do you want to try to get first? What appears to be the easiest thing for us to get? BC, great. How am I going to find that? Excellent. So what would I write then? Good. I'm going to write it as BC instead of A, but whatever. So far, so good? So to get the BC squared by itself, I'm going to subtract the 13 squared from both sides. Remember, like we said before, because of the order of operations, I can't just subtract the 21 and the 13 and just write it as 8 squared. I have to write it like this. And then just like before, to get rid of the squared, we'll square root. And then we'll go down to our calculator and do 21 square, or square root of 21 squared minus 13 squared. Yuck. Really? I can't see worth a hill of beans today. There we go. 1649 is our result then. Everybody okay there? Now let's look for one of these two angles, either angle A or B. Once we find one of them, we're looking good because we can just use subtraction to find the other one, right? But it's finding that first one that's going to be the tricky part. It doesn't matter which one we want to find first, so let's just say let's find angle A. Okay. Relative to angle A, the side that I know 13 is opposite, adjacent, or hypotenuse. Adjacent. And the side 21 that I know is opposite, adjacent, or hypotenuse. Hypotenuse. So which trig function am I going to want to use here? Cosine. Perfect. So we'll say cosine of A is equal to adjacent over hypotenuse. Everybody good to here? So we have to get that angle A by itself. So I need to get rid of the cosine that's in front of it. How do I cancel that out? Or how do I get rid of that cosine that's in front of the angle A? Victoria? Excellent. Inverse cosine, right? So I'm going to do cosine inverse to both sides. Because cosine inverse cancels cosine out. Remember from last semester, the inverse trig functions always return an angle measure. So it should make sense that angle A is equal to a cosine inverse of something, right? Because that's going to give me an angle value back. So I'll just go to my calculator. I'll do cosine inverse of 13 over 21. So 5175. Okay. And then to find angle B, what do I do? Yeah, I can just subtract them, right? What else could you do if you were so inclined here? I could also do the same thing that I did for angle A, just using angle B, and could find it directly using an inverse, but I'd rather do the subtraction because, boy, that seems like a lot less work, doesn't it? But it wouldn't be incorrect to do it that way. Any questions so far about what we've done? Okay. I want to point out one other little thing here before we move on to the next topics, and it's a check-ish that we can do on this. I don't want to call it a pure check because it doesn't actually tell you whether your answer is right or wrong, but it will tell you if your answer is absolutely wrong. So one of the things that maybe we remember from geometry, maybe we don't, but a fact that you could have talked about in geometry is that the side lengths and angle measures for any triangle are proportional. So that means that the biggest angle should be opposite the biggest side. The middle angle should be opposite the middle side, and the smallest angle should be opposite the smallest side. So a nice quick check that I can do for a problem like this is go, okay, so we had here A was 5175, B was 3825, and BC was 1649. So I have my biggest angle opposite my biggest side, my middle angle opposite my middle side, and my smallest angle opposite my smallest side. Now, just because that's true doesn't mean that those answers are necessarily correct. But if any of that part doesn't work out, it's absolutely wrong. There's something wrong going on. So it's a quick check. It doesn't tell you for sure if it's right, but it can quickly identify if something is really wrong. You know what I mean? Like if I transposed, like here, if I transposed like the 1 and the 7 and wrote 57.15, I just copied it down wrong, it wouldn't catch that mistake. But if I had like set up one of my trig ratios wrong and got like way wrong answer, it would catch that mistake or something. Or if I use sine instead of cosine, if I use the wrong trig function there, it would catch that kind of a mistake because you would not get the right answer then. Okay? Okay. So what we should be left with then is What about non-right triangles? What can we do there? In a non-right triangle, we have no Pythagorean theorem, and we have no Sohcahtoa. Woof. So we're going to need some new tools then to replace these guys, right? There's no other way about it, or no other way around it. We got to develop something new. So that's what we're going to be looking at in Chapter 7, is these new tools that we can use in these situations where we have no right triangle, or even if we have just a right triangle, these new tools still will work, but they're kind of trivial, like it's easier to just do these things in the past, or they'll reduce down to just these things that we've already done in the past. Of course. Okay. So in Chapter 7, we're going to look mainly at these two new tools that we can use in any triangle. The first tool is called the Law of Sines. I like to abbreviate that as LOS for Law of Sines. So what the Law of Sines says is if I have a triangle, and I've named this triangle ABC, and I named the sides now, so I'm going to name the angles with capital letters. I'm going to name the side opposite that angle with the lowercase letter. So, for example, angle A, the side opposite angle A is this side here. I'm going to name that with the lowercase letter a. Angle B, the side opposite is this one. That I'm going to name with the lowercase letter b. And then angle C, the opposite side is that. And I'm going to name that with the lowercase letter c. Everybody's okay with how we're going to name our triangle? Critically important that you're able to name your triangle in this way, because if you are not naming your triangle in this way, the formulas that we're about to give do not work. So we got to make sure that when we say side A, we're talking about the side that's opposite angle A. Is that okay? Okay. I just really want to emphasize that. Okay. So what the law of sine says is that sine A over A, that ratio is going to equal sine B over B, which is also equal to the ratio of sine C over C. Everybody's okay with that? It's a pretty simple formula, right? Now keep in mind, you don't need all three pieces. You can pick and choose any two to set equal to each other, and it's fine. Since they're all equal to each other, you don't need, sine A over A, you can write as equal to sine C over C, right? Everybody's good with that? Okay. Our second tool is called the Law of Cosines. I'm going to abbreviate that as LOC. So if we take any triangle and we name it the same way, this following equations all hold. Now keep in mind, this is really the same equation three separate times, right? If I just take the first equation, switch the A's and B's, it's the same as the second equation, right? Or if I take the first equation and switch the A and the C, it's the same as the third equation, right? So I'm going to write down all three versions, but really, it's the same equation three times, just with some substitution going on. What does this equation kind of look like? Should kind of remind us of something. Yeah, it looks like the Pythagorean Theorem, right? Except it has this little extra piece at the end. It's basically just a correction factor for not having a right triangle. If you did this with a right triangle, cosine of 90 degrees is 0. So that correction factor at the end just drops off and you have the Pythagorean Theorem, which is, okay, that's neat. Okay, so we have these two new tools, right? The next question that you should be asking yourself is, okay, Mr. Kulik, how do I know which one I'd want to use when, right? Before, when we had the Pythagorean Theorem and Sohcahtoa, it was pretty obvious when you'd want to use one versus the other. Here, I mean, I don't know, like they both seem like, how would I know which one I'd want to use? So here's how we're going to tell. You remember way back into your geometry class, when we talked about triangles, one of the things we talked about was triangle congruence and triangle similarity, right? That was something that you did probably a fair amount of proof with. And we had a bunch of triangle similarity or triangle congruence theorems that we used to do those proofs. You guys remember doing that? We abbreviated those theorems with like 3-letter combinations, like side angle side or angle side angle. Right? You guys kind of remember that? So we're going to use that same abbreviations to indicate whether I should be using the law of sines or the law of cosines, depending on what information I have at the beginning. So the law of cosines, we want to use when we have a side angle side situation or a side 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 situation. Now I'm going to put a little asterisk on the side 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 situation because there's one other thing we need to make sure that we're checking for in that situation before we go bowling right into using the law of cosines. But we'll deal with that here in a little bit when we get there. Probably not today, but I want to put a little asterisk there because it's a little bit special, that case. So the law of sines we use when we have an angle side angle, an angle angle side, or the SSA case, which again I'm going to put a little asterisk there on the SSA case because again there's a little bit of extra stuff that we have to do in that situation. If I go and I look at these 5 letter combinations we've written down, which one of them doesn't really fit? If you think back to triangle congruence and similarity, that's a big ask. The one that doesn't fit is the SSA situation. because if you think about it in the opposite order, it makes a square word. And I was pretty sure when I took geometry, there was no square word theorem, because I would have definitely remembered that because it would have made me giggle. So it turns out that there is no side-side angle congruence theorem, because it's possible in that situation you can have two triangles that have congruence, like the two pairs of congruent sides and then that congruent angle that's not included, and have two separate distinct triangles. Let's draw a picture and kind of see that. So I'm going to generate this picture with like this geometry software so that I end up with a nice picture. Yes, sir. Absolutely. You're welcome. All right. You go away. Okay, so this is, let me just put the thingy on here so you guys can see what we got going on. Let's do that. Okay, so this thing is 12 units long, and have this be 48 degrees, and I think I want that to go clockwise. Yeah, perfect. Okay. Okay, so what I have here is I have one side that's 12. I have an angle that's 48 degrees. So I used a line here to draw that angle, or that other arm of that angle, because, and then the circle I drew has radius 10. So I can make one triangle. Let's do it this way, actually. Here, so that's a 10, 12, and then the 48-degree angle. Everybody kind of see that? But I could have also made this triangle here, where I have a 10, the 12, and then my 48-degree angle. So that's why that SSA is not a congruence theorem, is because you can have two triangles that have that SSA property but are not the same triangle. Just put that on there. You guys see that? Now, does that always happen? No. I mean, there's situations where maybe one triangle is possible and it is, you know, the congruence does hold. There's a special case when that always happens, and you actually did have a theorem for that in your geometry course. That was called the Hypotenuse Leg Theorem, I think, in your textbook, if that rings a bell. That was the SSA situation where the A is a right angle. If the angle there is a 90-degree angle, then it turns out that those two sides are basically the same side, and it's just one triangle. So that one specific situation there, the SSA situation, is going to be very tricky to deal with. Okay? Because you can get multiple answers in that situation. But that's a little bit down the road here for us. Okay. So first thing I want to do before we get going any further is I want to draw some pictures and make sure that we're able to pick out whether we have like an ASA, an AAS, an SAS, an SSS, an SSA, that we're able to look at the picture and identify what's going on. Okay with that? All right. All right, so let's say that we have that side is given, that angle, and that angle. So I'm just going to highlight the stuff that would be given to us. So which situation is this? Okay, angle, side, angle. Are you sure it's not angle, angle, side? Okay, right. And this is why we're doing the example, is to make sure that we know which one is which, right? This is angle, side angle. You were right. So that's good. But the natural question is like, okay, how does that look differently from angle, angle, side? That's what angle, angle, side is going to look like. So notice in angle, side, angle, the side there is an arm, is part of both angles. In angle, side, the side is a part of only one of the given angles. So you guys see the difference there? Yes? We're okay? Okay. Again, that's important that you're able to do this because this is the major way that we're deciding which one to use. How about this one? Is this SAS or SSA? Clearly there's two sides and an angle, so it's got to be one or the other, right? It is side, angle, side. Again, you notice that the two sides that are given are both a part of the angle that's given. That's the side, angle, side situation. An SA situation would be something like this, where one of the sides is not a part of the angle. And this is the one that's really critically important that we're able to tell the difference between, right? One of them we should use the law of sines, the other we should use the law of cosines. So it's really important that you're able to tell the difference between these two. Yes, absolutely. And then the last situation is the one that nobody can possibly screw up. What's this? It's got to be SSS, right? There is no confusion there on that one. That's the one everybody's hoping to get. It's like, oh, okay. Whew. I know exactly what's going on with this one. Okay. Do we feel pretty good about picking these situations out visually? All right. so let's go ahead and look at some specific examples now and start using these law of sines and law of cosines to do some stuff. Sound good? So here, we're asked to solve the triangle whose angle A is 32 degrees, angle B is 73 degrees, and side C is 13 inches. What's the first thing I'd want to do in this sort of situation?
Get the third angle.
Okay, I mean, even before that, I'd want to draw the picture because that's how I'm going to determine whether I'm in an ASA or AAS situation. But then I would certainly, the next step for sure, let's get that third angle. So I'm going to go ahead and draw and label my triangle. Notice that when I labeled my side lengths, I used that naming convention that we talked about earlier, where I named the side opposite the angle with the lowercase letter. Everybody's good with what I've drawn here? Okay, is this ASA or AAS? This is ASA. Everybody can see that? That tells me that we're going to be using the law of sines. So far, so good? Okay. So we need angle C, we need side A, we need side B. Here, oops. The order absolutely matters that we're doing this. There is the first step that we must do is, as Rami suggested, we have to find angle C. But that's really easy, right? We have the other two angles. So that's just 75 degrees. Feel good? Okay. Here, solving A or B doesn't matter in this case. So let's solve, for the sake of argument, let's solve for angle or side A first. Okay with that? So using the law of sines, one of the ratios I need to pick is the one where I know both the side and the angle, right? Because the law of sines is sine A over A equals sine B over B equals sine C over C. So first thing I want to do is figure out which one of those ratios do I know both the side and the angle for. Well, it's C, right? And then if I'm looking for side A, I'm going to say sine C over C is equal to sine A over A. Everybody's okay with that? Now I'm going to just solve this for A. So I'm going to start by cross multiplying. So a times sine 75 equals 13 times sine 32. Everybody's okay with that? And then we'll divide both sides by sine 75. And go to the calculator. So I'm going to use the fraction option so I don't have to worry about goofing a parenthesis or something. That way I can write it exactly like it looks like on my sheet of paper. Feels safer that way a lot of times. So I get 713 as the answer there. Everybody feel okay doing that? Not too bad, right? How do I get side B? Can I use the Pythagorean Theorem? I know two sides.
No.
No, why not? It's not a right triangle. What do I have to do instead? I'm just going to use the law of sines again. I'm just going to do sine C over C equals sine B over B. Everybody okay with that? And I'm going to do the exact same thing. I'm going to cross multiply and then divide by sine 75, and we're all done basically. So 1287. I feel okay? And then real quick to just kind of check things. I got the smallest across from the smallest, the biggest across from the biggest, and the middle across from the middle. Looks pretty good, right? Okay. We'll stop here. This feels like a natural place to stop. We'll pick up with some more examples next time as we just kind of continue to work through some of the weird things that can happen. This was a pretty basic situation where nothing strange occurred. But we still have a lot more examples to kind of burn through. That'll be most of next class. There's no assignment that's going to be due on Sunday. So any work we might have assigned, I'm just going to push into next week. Conceivably, I guess you could start on like 1 through 4. You could conceivably work on, but I don't even think you need to do that right now. I'd rather have you wait and see some more examples before you started. Of course.